Now we're going to study what's called Archimedes Principle. As we learned before, this is the cardinal principle behind building ships. What does Archimedes Principle tell us? Well, common sense tells us that if you throw something into a fluid, say water, the fluid will exert a force on that object submerged in it. And there is an upward force, which is called the force of buoyancy, okay, or buoyant force, F of B. The Archimedes Principle tells us what that buoyant force is equal to. So what is it equal to? Well, suppose I drop something into a bucket of water. Okay, this thing is denser than water, so it sinks. This water is in a container with a spout, and it's filled all the way to the very opening of the spout, so that when you drop this thing in, water is going to come out. Okay, so water is going to come out. How much water comes out? Well, the amount of water that comes out, okay, the volume of this much water, of course, equals the volume of the block that we dropped in, right? Because, this is all the volume the container can hold. Now, if we weighed the water that came out of the water container, okay, it turns out that the force of buoyancy exerted on this block actually equals to the weight of the water that's being displaced. How do we know that? Well, we can weigh this thing in air, okay, and we can also then weigh this thing in water, okay, with a tension. It turns out that the weight of this thing in air is greater than the weight of the same thing in water, because the tension here, which is the parent weight of this object underwater, is lower than the original weight by how much? Well, by the force of buoyancy, of course, because you got T, you got buoyancy force, and of course you got the weight, right? These three forces balance out. And it turns out that this buoyant force, which is equal to the weight of the object in air minus the weight of the thing underwater, it turns out that it is actually equal to the weight of the water it displaces. This is something general, which is called the Archimedes Principle. Basically what it says is that the buoyant force equals to the weight of the fluid displaced. Okay. Here in this case, the entire block is submerged in water. It therefore displaces a volume which is equal to itself, and the weight of this much water, not the object itself, but the weight of this much water equals to the buoyant force. If I express it in mathematical form, the weight of the fluid displaced, that will be density times volume times the acceleration gravity, rho fluid times the volume, that is the volume displaced, volume of the fluid displaced, okay, times g. That is the so-called Archimedes Principle. Now, we don't really know how Archimedes got it because he had no physical formulas that we know today, all these modern formulas in physics. So he must be very, very wise. But what we can do with today's knowledge, we can easily derive the so-called Archimedes Principle. And here's how it goes. Suppose I drop this block into a fluid, say water. Okay, it is being therefore pushed around by pressure from all sides. For simplicity, let's assume that this is a regular block with straight sides. Okay, there is a top surface, there's a bottom surface. I'm not going to worry about the pressure on the side because we know the block is not going to move to the left or to the right. I'm only going to worry about the vertical force. There are two surfaces, the top one and the bottom one. Those are the two surfaces I need to worry about because I want to figure out the force provided by the surrounding water to these two surfaces. Okay, at the top there is a force which is equal to the pressure at the top times the surface area, right? At the bottom there's also a force, but this force is due to the pressure at the bottom times the same surface area A. Now, what is the pressure at the bottom? Remember, the bottom surface is below the top surface by how much? By a depth h. We learned that anytime you go down a distance h, the pressure of the fluid should increase by an amount which is equal to rho gh, rho being the density of that fluid, right? So therefore, the pressure at the bottom would be P, which is the top pressure, plus an additional value, rho fluid gh. Right? We take that pressure, we multiply this by the same area. So that is the net force pushing it. That is the force at the bottom pushing it up. So what is the net force pushing this block up from the surrounding fluid? That will be upward force minus the downward force. So the net force is P plus rho fluid gh times A, okay, minus PA. Now PA and PA cancels out nicely, and what do we have here? We only get this term left, rho fluid gh A, right? Now take a close look at h times A. What's h times A anyway? A is the surface area, and h is the height of this block. Therefore, A times h is just the volume of the block, which is under water, rho fluid gV, and that is the mathematical expression of Archimedes' principle, the buoyant force. So, basically this is saying that the physical origin of the buoyant force is a higher pressure pushing a block or any object submerged in fluid, pushing it up from below, and a lower pressure pushing it down from above. There is a net force, therefore, going upward. That is due to the fact that the deeper you go in a fluid, the greater the pressure. Okay, so there is the reason why you have a net force going up, and that's called a buoyant force. The Archimedes principle can help us decide whether something is going to sink or something is going to float. Let's say we drop something into water. Okay, you know if this thing is light enough, it's going to float. When it floats, it only displaces part of its volume, right? This part of the volume, only this part of the volume is submerged underwater. We call it V sub. According to Archimedes' principle, how much is the buoyant force exerted on it? Well, that would be the buoyant force, right? That would be equal to, okay, density of the fluid times G times what? Times the volume of the fluid or water being displaced, that's V sub, right? Not the whole volume, because that part of the volume is above water. Meanwhile, there is its weight, right? W, F, G, or W. That equals what? That equals to the density of the, that basically equals the mass of the object times G. The mass of the object is its density, that's the density of the object, not density of the fluid, times the whole volume V of the entire object, right? And then times G. Now, this thing is in equilibrium. It doesn't go up, doesn't go down, and therefore the buoyant force must equal to the gravitational force. So therefore FB equals FG, and we equate these two, we find V rho fluid G V sub, okay, equals to rho object V G. You cross out G and you can find a ratio V sub over V. V sub over V equals to rho object over rho fluid. Let's take a good look at this formula. This is the percentage or the fraction of the volume that's submerged underwater. Now, if something floats, then only part of its volume is below water. So this ratio will stay below 1. But on the other hand, we know this ratio is rho object over rho fluid. So what does that tell us? For an object to stay only partially submerged, in other words, it floats, we want to make sure that the density of the object must be lower than density of the fluid in which it is submerged. For example, you throw a piece of wood into water. In most cases, wood has lower density than water, therefore it floats. Okay. On the other hand, if you throw a piece of iron into water, you know the density of the iron, which is of course rho object in this case, is greater than the surrounding water, therefore this ratio is greater than 1. But that would require the ion to submerge more of its volume than the entire volume it possibly have. So this ratio would have to be greater than 1 to make it float. We know that's not possible because you cannot submerge more volume than you have, right? So therefore, the iron block is going to sink, and yet the wood block is going to float. So again, from Archimedes' principle, we learned that the condition for an object to be able to float in a fluid is that its density must be lower than the fluid in which it is submerged. A special case, an interesting special case, is when rho object equals rho fluid. Okay, so the object has exactly the same density as the fluid. If that is the case, you throw this object into the fluid, what happens? Well, this ratio has to be equal to 1, right? Which means 100% of that object is below the fluid. And yet, the net force exerted on it would have to be equal to 0, because indeed, when these two sides are equal, both are equal to exactly 1, you have FB equals FG. Therefore, it is not going to sink to the bottom, rather it's going to stay where it is. Okay, the net force is equal to 0. It can be balanced anywhere inside a fluid as long as 100% of its volume is submerged. Can you think of the application of something like that? Well, if you were a fish, okay, what do you think you want your density to be? Do you want your density to be higher than the surrounding water? If that is the case, you're going to go up, right? All the way to the surface. In fact, part of you will be above water. Do you like that all the time? Well, probably not. On the other hand, do you want your density to be lower than that of water? Do you want to go all the way to the bottom and stay there? You probably don't want to do that either. If you're an average fish, you probably want to be able to, just swim anywhere in the water. Wouldn't it be nice if the buoyant force of the water balances your own weight so that you can be anywhere you want? Well, it's doable. All you have to do is to make sure that your density, the density of the fish, equals to the density of the surrounding water. And how does that work? Well, you can actually adjust your density. Okay, fish has the ability to do that by controlling the air pockets in your body. That's how you vary the density. In fact, a submarine does exactly the same thing. A submarine has water compartments, okay, has individual water compartments. When a submarine wants to dive, what it does is that it opens up these water compartments to allow water to go in, and therefore the density of the submarine becomes greater than the density of surrounding water. It goes down. How does it float back up? Well, all we have to do is to pump the water out of these compartments so that the compartment is now made of air instead of water inside, and that lowers the overall density of the submarine below that of water so that it floats back up. So that's how a submarine works. Okay, so that is Archimedes' principle. I want to call your attention to an interesting problem related to Archimedes' principle. Suppose I have a container with a certain kind of liquid called liquid 1, okay, and I drop something in. This object has a density that is lower than liquid 1, therefore part of it is going to be submerged. What I want to know is what happens if I add another fluid, okay, on top of fluid 1. Let's assume that's fluid 2, and fluid 2 and fluid 1 do not mix. Let's say this is water and fluid 1 is oil. Okay, it is a type of fluid that's lower in density than water, therefore it stays up and it does not mix with water, so it stays up like this. Okay, so this is fluid number 2. Okay, here's my question. My question is, before fluid 2 is added, let's say a part of this object is inside fluid 1, the other part is in the air, right? Now, as I pour fluid 2, suppose fluid 2 is less dense than both this object and fluid 1. Okay, so the object will not be able to float all the way up, right? Rather, it's going to stay somewhere between fluid 1 and fluid 2. Part of it is in 2, part of it is in 1, right? My question is, as you pour fluid 2, say oil, what's going to happen to this volume? Is it going to increase or is it going to decrease? In other words, this object here, Does it go down or does it go up as a result of adding fluid 2 into the mix? What does fluid 2 do to it? Well, you know, here is the contact surface between the object and fluid 2, right? And fluid 2, of course, is going to give it some pressure. There's no question about it. Okay. So, what do you think? Is the thing going to go further into fluid 1 or is it going to go up or stay where it is? From this consideration, it looks quite obvious that this object will have to go further into fluid 1 because after all, fluid 2 is pushing it down, right? But on the other hand, you say, no, wait a second. Isn't it true now that this object also receives a buoyant force, which is equal to rho v2g? Here's v2, okay? The part of it that's in fluid 2, and here's v1. Isn't it true that you must add these two buoyant forces up in order to get the total buoyant force? Now, you just add some buoyant force, right? You didn't increase the weight of the object. Therefore, shouldn't this thing go up a little bit because you don't need to get that much buoyant force from object 1? Because object 2, fluid 2 is coming here to help with an extra buoyant force. It looks like we have a contradicting result, contradicting prediction. On the one hand, we know the pressure of fluid 2 will push it down. On the other hand, we know the buoyant force, if you use the Archimedes principle, from fluid 2 will push it up. So, what really happened? Does it go down or does it go up? Okay, there's an interesting question to think about. Now, let's see. How do we resolve this problem? It is certainly true that on this contact area, fluid 2 pushes it down. But let's take a look. Is this all fluid 2 does to the situation? When you add fluid 2, does that change the pressure in this object, in fluid 1? Well, the answer is yes, of course it does. Okay? So as a result, you have an additional pressure greater than before due to the addition of fluid 2. Okay, so indeed, on the one hand, you have pressure coming down. On the other hand, you have an additional pressure pushing you up from fluid 1. And if you do this calculation, it turns out that indeed the weight of the entire object is now equal to rho 1g v1 plus rho 2g v2. You can easily do this calculation. If you assume, for example, this is just a cylinder, okay? The cross-section area is the same. Just simple geometry makes the calculation easier. This does not mean that that fluid 2 actually gives it a net force going up. No. Fluid 2 gives it a force going down, okay, from this contact area. But the introduction of fluid 2 increases the pressure inside fluid 1. So fluid 1 gives it a further upward force. Okay, this is the reason why the thing actually going to go up a little bit, because you have this additional term. Okay, so fluid 2 does not give a lifting force to the object directly, but it does that indirectly through an additional pressure on fluid 1. So this is an interesting observation. So what is the answer? The answer is it's actually going to go up a little bit, okay? Because when you add the second fluid, you have this extra term. Here's the weight of the object, which never changes, which means this term is a little bit less, which means V1 is lower than before. In other words, it is going to go up a little bit. All right, so this is an interesting application of Archimedes principle. Now,